Yes. Okay. You will introduce yourself.
Good morning. We are going to start with the session 8A TCCMA. The first presentation is entitled Coding Cross-Sections of an Electron Charge Transfer Process, Analysis of Different Cuts for the Entrance and Exit Potentials. The presentation is in presence, and the authors are Noelia Faginas Lago, Emilia Valenza Ferreira de Aragao, Luca Mancini, Marzio Rosi, Daniela Ascenzi, and Fernando Pirani. So the article will be presented by Professor
Noelia Faginas Lago.
Okay, so let me share your presentation. Okay, one moment, please. I just want to check something. Yeah, don't go. Okay.
Hello, everybody, and I am Noelia Faginas Lago, and I'm from Department of Chemical Biology and Biotechnology from University of Perugia in Italy. Today, I would like to present you a code right in our group, where this code is the goal of this code is to evaluate the cross-section of an electron charge transfer process. So I presented the code to analyze of different cuts of potential energy surface for the entrance and exit potential. Okay, so the idea of this presentation is inserted in a more bigger project. This project is an astrochemical origins project where study the molecules present in the interstellar medium. In the interstellar medium, you know that there are more about 270 molecules species detected by the astronomers' detections. So these molecules are composed at least for 6 atoms, and these molecules contain some heavier atoms like nitrogen, carbon, and so on. So what is the goal of this part of this project? The goal of this part of this project is how can we explain the formation of these molecules? So from a part there are the astrochemical models. The astrochemical models are the databases like CAIDA and other databases that contain the data about the amount of these molecules are contained in the gas phase or another dust grain or surface catalyzed reactions. But the important thing is that the astrochemistry needs the information from chemistry about the cross-section, the Breching ratio, and the percentual, the amount of this species in the interstellar medium. So, to do it, we need to do the abelian calculations to develop a potential energy surface. But in some reaction, do you think that in the interstellar medium we have a temperature, a very low temperature? We are speaking about 10 Kelvin, and in this case, the astrochemical models are not able to do this calculation. So the astrochemical models combine the observational data, abundance of species, and experimental data to evaluate the product Breching ratios and rate coefficients. But they have the models, so the astrochemistry needs the exact, the ab initio calculations to do this comparison. So the theoretical data. So we need to evaluate the possible pathways, the reactive channels, and the product ratio rate coefficients. Okay? To obtain the rate coefficients. So, what happened? In the case of the ion neutral reaction impulse, we have observed that there is a charge transfer step. And this is a problem, or this is more complex to evaluate the debration ratios. So why? Because, for example, in this case, we have DME is the dimethylated that reacted with the helium cation, and we obtained the dimethyl cation plus helium neutral. So here in these reactions occurs a charge transfer. So if you analyze the formation of a new chemical species, in this case you can observe that it is not a single pathway. You need to analyze the intermediates, transition state, and products for the different pathways that we will see now. So in this other case, we observed the fragmentation of the newly formed ion, that is, the molecule of the methylated, in this case, is a cation. So the helium cation transfers the charge to our neutral molecule. Our goal is evaluate theoretically the cross-section and the Bayesian ratio. Please. Okay, thank you. Okay, so in the case of the ion neutral reaction involving the helium plus, first of all, we needed to, this is a prototype reaction. Why? Because the helium, the first ionization energy of the helium is higher, 24 around electron volt. Here we have the dimethyl ether, and this is our, we will see in the next slide, the orbitals where we can transfer this electron. So, and we take care about three different types of orbitals. The orbital of 2b2, 4a1, and 2b1. Why? Because our objective is calculate the cross-section from the global electron transfer process, compare these results with the measured, the experimental measured as a function of the collision energy with a molecular beam technique, and then evaluate the related reaction rate constants. Today, I would like to present the code that we developed to evaluate it. Please.
Sorry.
Okay. No, before. Okay. Okay. No. No. Before.
Before. Sorry.
No. So maybe I did it. Okay. No. Okay. There.
Yeah.
Okay. 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 So first of all, to start the user, the computational user, before to start to analyze the different cuts of the potential energy surface for the entrance and for the exit reaction, we needed to define a representing of our system in the space. So we represent our molecule that is in a three-dimensional space, and the molecule is given by the effective atoms. So is the blue atoms. This is our molecule. Also, we represent the center of mass of this molecule that is given by the red bond that gives the center of mass. Okay, and it is in the origin of the Cartesian reference systems. So in our code, we put the position, in this case of the helium of any ion, is declared in terms of the spherical coordinates. In these spherical coordinates, we have the uppercase R that gives the distance between the ion to the center of mass to our molecule, neutral molecule, and we have the theta angle that gives the angle between the R vector with the Z axis, and the phi that is the azimuthal angle. So first of all, the user needs to define the system in this reference. Okay, first of all, we need to optimize the geometry of the molecule with ab initio methods. We have the same system in the x, y plane, and we need to define the positions, the three positions x, y, and z for the effective atoms. If you observe, this position is given by the position of each effective atom, where n, big uppercase N, give the number of total of the effective atoms, and the m is the total mass. Obviously, what it means, we need to define the movement of this helium, this ion with respect to our molecule, neutral molecule. So it gives that we define the x, y, and z prime, what is the reference of the position respect of the center of mass. You can move that. Okay, so here in this system, before to start, we need to represent this. Our ion is given in this the following formula because it's given with the spherical coordinates. So we need to evaluate the distance that is given by this between the position of the ion respect to each effective atoms of the neutral molecule. Okay? So here we enter in the code that we have developed. This is the general code. In this code is called pes.c, is written in Python, and this is the general scheme. In this scheme, you can observe that the green blocks are the inputs, the gray blocks are the outputs, and the blue blocks that we will see are the piece of code that you need to evaluate, separate, but are not included in the main program. So, you can observe that we need to give an input that is the big R, theta, and phi. Theta can be varied from 0 until 180 degrees. And phi can vary from 0 until 360 degrees. We need a fixed R, and with this we give this type of input, and we need to obtain the position of the X, Y, and Z for our cation. Okay, so at this point we obtain a file that contains the Cartesian coordinates of an atom of the molecule. We have all coordinates, and it come back and the returns Cartesian coordinates of the ion. We have the molecule and we have the ion. At this point, the goal of our code is evaluate the entrance potential and the exit potential. So you can see that here we call this part. For the entrance, we have the molecule, neutral, and the ion. We need to evaluate the electrostatic and non-electrostatic part. Instead, for the exit potential, we need to evaluate the van der Waals and the induction. Obviously, you can put attention because in the exit channel, we have in this case that our molecule now is a charged molecule because the helium, the cation transfer the charge to this molecule. Okay, another data that Another data that we need is the partial change of the atoms of the molecule for the electrostatic part. The electrostatic part, how of each of these blue boxes are evaluated separately. The electrostatic part is evaluated using this formulation where that is the Qi is the charge, the partial charge of the atoms for each molecule, and the lowercase r ij is the distance that we have seen previously to between the ion with each effective atom, and this given at a distance of big R. Okay, in the case of the exit channel, we needed to introduce the induction because in this case it's very important that we take care about this induction. The induction is given like by this formula. We have take care about the alpha neutral because we have now that our ion is not one ion, but is neutral. We have take care about the polarizability. Now we will see how we obtain these two parts that we use the same formulation. When we finish the general code, we obtained a list of values where we have the entrance potential as a function of the uppercase R, theta, and phi, and an exit potential. So, okay. In the case of the non-electrostatic part, we needed to analyze the interaction between all of these, the sum all of these interactions. So between the ion with each effective atom. We use this formulation. This formulation is a potential developed in our group. It improves Lennard-Jones potential. This potential is very similar to the classical Lennard-Jones, but take care that about the behavior of the environment of our system. This formulation is given if you can observe about well that you know, okay, and there is a constant that is m. This constant can be the different values. 1, 4, 6 depends of the interacting molecules are neutral ion, or ion dipole induced. In this case, for the entrance potential, m is equal 4, and for the exit potential, m is equal 6, because we have seen that there are charge transfer. You can observe that here there is an exponential part that is given by this formulation. That is the formula that modulates the value of the interacting partners, take care about the environmental of our particles. If you observe the non-electrostatic potential is given by the same formula that the van der Waals potential. One for the entrance code and one from the exit code. Okay? Okay, so this is we can move because we have seen before the electrostatic and the induction part. Please. Okay, so at this point we arrive to when we have defined the general program. Here we can evaluate the potential energy effect curves as a function of big R. If you remember, the uppercase R is the distance between the ion respect of the molecule in the entrance and the helium, in the case neutral, respect of the molecule that in the exit channel is charged. Okay, also the colors are the code is the same, green input, gray output, and these are the conditions that we need to evaluate. Okay, so we need to here give to the code some inputs, theta, phi, and d, and asymptote. What is asymptote? The asymptote is evaluated with the difference. Sorry, yes, I need to come back to here.
Okay, sorry.
Yeah, because it's a little complicated. So the asymptote we evaluated with the difference between the first ionization energy of the helium respect of this energy. So we can try to do the calculation with the 3 possible asymptotes to obtain, because our goal what is? Obtain the crossing point between the potential entrance and the exit entrance, but this crossing point can be happens at the exothermic. So when you obtain it, you can visualize and analyze the charge transfer. So that is the difference between this value with this, and with this. We obtain three types of asymptotes. So in this case, this is an input value that we need to do. At this point, the code open two blank files, output files, and we define the distance. In this case, we have defined the distance between an interval 1 angstrom until 12 angstrom. Obviously, you can modify, but these are the distance that can be evaluated a lot of intervals, from 1 to 12. Here you enter in a loop and you evaluate with a step of the 0.001 the Q entrance and the Q exit. And these potentials are brightened in the output file 1 and the output file 2. So we have the value of R, the Q entrance, Q electrostatic, and Q not electrostatic for the entrance and the exit. After that, when we evaluate these types of potential for the entrance and the exit, we can open output file 3. This output file 3 contains the coordinates of our system that give us the opportunity that we can use in Avogadro when we visualize our system. At this point, we can put a distance that we decided to frozen. So we decided, because we evaluate an interval of the big R, that we put an interval of the distance, we give an input value. This input value can to choose and depends of your systems. So in this case, was bid for the 3.5 angstroms, and we obtained our coordinates at this distance for our system. At this point, we close these files X, Y, Z that we can visualize. Okay? Okay. In the same way, that is our part of this goal, we can evaluate the potential energy surface as a function of the theta and phi. What it means that we put a theta or phi fixed and we vary in a very huge range the other angle. How you can see, these are the part of the code that you needed to choose if you want to vary the phi or vary the theta, and you obtain the variation of the entrance and exit potential changing the theta and phi angles. Remember that the theta is the angle inclination of the uppercase R vector respect of the Z axis, and the phi is the azimuthal angle. This is the colors are the same. We can vary obviously the blue box using the formulated that we have seen before. Okay. This is the final part of the code, because here we analyze the crossing points. So we have evaluated the potential of the entrance, the potential of the exit, and we need to obtain, if we obtain it, the crossing point where these two curves close. Okay? So this is the whole piece of the code that we have seen before together for the phi, for the theta, and here we have used the dissection method. The dissection method is where we analyze using three values, A, B, and C, to obtain where we have defined this ratio. We have obtained using a general function. So, okay, here I would like to show you an example of results. Here is for the helium and the methyl benzene. Here you can see that the green line is the entrance potential, and this given we care about the first ionization energy is there. Here is the exit potential using the HOMO orbitals of the dimethyl. And you can we go? One slide. Okay, so you observe that there is not a crossing point. At this point, we have used the other types of orbitals to transfer this electron transfer, and here you can observe that we find crossing point with the entrance in green and with the 2b2 orbital. Okay, so at this point we have this crossing point at this distance, and we obtained the interacting potential that gives us the opportunity to evaluate the crossing section. Okay, so to conclude, so this is a part of the code in a very big program that was applied for 3 systems. So the helium plus with the methyl ether, methyl formate, and methyl. We can reproduce with this the experimental data, and we have the advantage in relation to classical capsule models. Sorry, why? Because first of all, estimate of the initial molecular orbital from which the electron is captured from the atom. Because you can see that in the HOMO orbital is not possible. Allows to visualize the formation of the collision complex. And this type of model estimated the reaction rates as a function of the temperature. We have also compared with the experimental result, and we obtained a very good comparison to obtain the cross section like a benchmark data. So to conclude, I would like to thank the project that are the cluster that we can use to run the calculations, and the Fondazione Peruvian CEMI, that is the Centro di Eccellenza Materiali Innovativi e Nanostrutturati, that funded this research. Thank you very much. If you have some question.
I have just a small question.
Yes.
First of all, thank you very much for your talk. Do you have any, in your team, do you have any people from computer science or?
Computer science in the same person. So in our team,
codes and so
no, the persons are chemistry, but the background are computational chemistry.
I'm asking because in Brazil it's quite hard to find people inside the chemistry departments that sometimes.
Yes, also we collaborated with the computational science person, but not exactly in this project. In this project was developed only, I think, if I remember right, only chemistry.
What's the computational cost to run this project?
So this code writes 80,000 lines about each configuration in 28 seconds. It's very fast, 28 seconds, for a very, very full range of the interactions. We evaluated from far to short distance, and each angle, 28 seconds. Yeah, but this. So don't need complicated libraries. This diagram.
I'm asking because normally when you do something,
Yes.
it's quite heavy.
Yes, but it's optimized. Thank you. Thank you.
We continue with the next presentation.
If possible, put it, because we can move the slides.
Yes.
Sorry.
Yes, we try it. Please, because it's better.
Okay, so we open
Okay.
this.
First of all,
You are the chair, okay?
Yes, yeah, he is the chair. No, no, I try only the pointer.
to show
So
this
it
show
works.
entire
That
screen.
is
Entire
Click
go
on the
before
preview of the
this.
screen.
Okay, it works.
Confirm by clicking share.
Yes.
Then we go here.
Why it shows all this?
Because it is sharing our screen, which is sharing our screen. Then view and full screen.
Okay.
There we go.
Oh, works. Okay.
We are here. And you are here.
No problem, no problem. Okay, so let's move to the next talk, which is delivered by Marcos Quines. And the title is Guided Clustering for Selecting Representative Samples in Chemical Databases. Please.
Okay, thank you very much. I'm Marcos Quines. I'm an associate professor in computer science at the Federal University of São Paulo. And this work was mainly developed by my master's student, my former scientific research student, Felipe Caldeirão, with the cooperation of Professor Juarez da Silva from the University of São Paulo and his former postdoc, João Paulo Jobim. Here's my outline of my presentation. First, I will contextualize this work inside the big picture of our project named Center for Innovation and New Energies. And then I'll talk a little bit about how to select representative samples from chemical database. I will introduce our proposal to perform the guided clustering selection approach. Finally, just some insights, some results from 2 data sets that we have used to do the experiments. And finally, some concluding remarks. This work is part of the CIN, which is Center for Innovation and New Energies. It's a large center in Brazil. It's about 300 members among faculty and students. And it's funded by the Shell company and also our state agency, FAPESP. This center is divided in 4 main divisions. 3 of them are experimental divisions, and 1 is the computational division, which is the computational material science and chemistry division, coordinated by Professor Juarez. And inside this division, which I'm one of the members, we have the machine learning group, which is composed by me, Professor Ronaldo, and also Professor Juarez. And our role here is to provide some support, data analysis, data mining support for chemistry and material science research in general for the whole scene, for the whole center. And besides that, we want to develop models for predicting materials properties and also designing materials, for example, using generative machine learning models. But what is representative selection? Given a large data set, we want to select just a few samples in order to evaluate these samples in deep and try to characterize the whole data set using just these few samples instead of need to analyze all the samples that we have in the data set. So how to select the samples in a given data set? Starting from the hypothesis that similar samples, similar molecules, for instance, with almost the same composition and the same structures might have the same set of properties or close properties. If you have a very dense group of molecules that are very similar, maybe if you just take one of these molecules and evaluate it, we can get some insights on how all the molecules inside this group can behave. And for that, you can use several clustering algorithms, for example, the KDs, and several other algorithms that we have in the literature. But why do we care with this type of selection? We have several problems at sea that might use this type of approach. For example, if you have like 100,000 molecules that in our chemical space that we want to evaluate using the FT calculations. Sometimes it's not possible to do that due to the computational cost of the process. So instead of performing DFT calculations in all the molecules, you can select just a few samples that represent all the groups that we have in this data set, and perform the DFT calculations in these molecules, and then try to extrapolate the results for the whole data set. Or also, obtain the most representative morphologies when studying nanocluster phase transitions, for instance. But before using machine learning in chemistry data sets and material science data sets, we need to characterize a sample. Or it means we need to get, for example, the XYZ representation of the molecule and convert it into a feature vector representation that is suitable for machine learning methods. We have several ways to do that. In the literature, there are several descriptors, several fingerprints that we can take from the molecule, from the material. For example, the code matrix. We start from the molecule itself, compute the code matrix, and then from the code matrix, you can use the eigenvalues to compose that feature vector that will feed the machine learning model. But we have a question here. Are all these features, like all the eigenvalues of the code matrix, equally important? It's not always the case. Sometimes you have features that are more relevant for specific properties and some other features that do not bring some useful information to study specific properties. So we need to be careful with that, not just characterize the samples into the feature vector, but which features are more important, in particular when we are dealing with clustering. But let's forget for a while that we have this possible difference between different features. How can we select representative samples in a general context? We can first characterize the data. We can characterize the data using specific features, for example, the eigenvalues of the code matrix, and then apply some clustering algorithms, like the k-means, as I mentioned before. And once you have the clusters, we can select one or a few samples from each cluster and use the samples as prototype of the cluster group. Analyze just this prototype, this representative selected samples, and then try to extrapolate it for the whole clusters. But what's the problem, as I mentioned before? The clustering process considers the distance between samples. And if you do not attribute specific weights for specific features, the distance might not reveal the reality we are searching for. So sometimes we need to enhance the weight for specific features and also reduce the weight of other features that are not relevant for the study. So to do that, to take into account this type of weighting procedure for each feature, here we propose a guided clustering method. It's a toolbox, can be used for any type of chemical, not any type, but several types of chemical data sets or material science data sets. And this tool provides sensible suggestions for the number of clusters, which is sometimes it's not easy to say a priori how many clusters, how many groups we have in this data set. So we use several score measures, for instance, the silhouette score, to try to estimate a good number of clusters, good number of groups for a specific data set. And we also optimize the features, as I mentioned, to highlight properties of interest. It means you can take the knowledge from the specialist and maybe the specialist say that this feature is more important, this feature is more important, and I want to group the data set, select the representative samples from this data set, using any specific feature or any specific properties from these molecules. So instead of using just a regular unsupervised clustering algorithm, we can put the information from the specialist into the loop. The method itself consists of two major steps. It's a clustering step and an optimization steps. So by starting with the initial weights, in which we attribute one for each feature, means all the features are equally the same. We cluster the data, find the groups, and then we calculate the variance intra-cluster for a given property that the specialist provides to us. For example, I want to cluster to calculate the variance, the energy variance inside each of these groups. And then we perform optimization of the weights in order to reduce the variance that we can find in each cluster performed by this clustering method. It's worth noting that we could use any type of clustering method here and also different types of optimization methods. For this work in particular, we use the k-means here and the Bayesian hopping algorithm to optimize the weights. And then we keep this loop, updating the weights, generating new clusters, evaluating the variance intra-cluster until you reach a desired homogeneity inside the cluster or a maximum number of steps are achieved. So here, just some results. We applied to several data sets. Here I brought two data sets. One is the evaluation of copper nanoclusters with 55 atoms. We have a total of 1,048 optimized structures using molecular dynamics, which is described in this paper. It's also our paper from Professor Graves and other colleagues. And after evaluating this data set with our method, we found that 14 clusters is a good number, which means we have 14 very specific clusters inside this whole data set. And here we have the pictures of all this representative selected from this 1,000 samples. So it means cluster 0, this structure can be used to represent all the group clustered together with cluster 0. And like this figure, this nanocluster here can be used to represent all the structures that are clustered with cluster number 12, and so on. I'm a computer scientist, so I cannot evaluate this in deep. So my colleagues from chemistry evaluate this, and they find very interesting outcomes. For example, we have 4 clusters with lower energies, and 3 of these 4 clusters are very specific. For example, we have one cluster with isomeric shapes, another cluster with pseudo-tetragonal shapes, and other cluster with decahedron shapes, which are very stable shapes according to them. Here it's another type of material that we have considered to evaluate our method. It's a series zirconium oxides, but we vary the proportion of serum in zirconium using this formula here with N between 1 and 15. And after applying the method to this data set, we found, using the C-rate score again, that 18 is a good number to represent all the data that we have in this data set here. And in comparison to the unsupervised approach, we reduce the total intercluster variance in 24% in comparison to the unsupervised approach, which means our clusters using the supervised guided approach is much more concise, much more homogeneous. So each sample, when we take the representative samples from each group, we might say that this sample represents better the group in contrast to the unsupervised approach. Here just some points. For example, when n is equal to 15, we obtain 5 clusters for a single type of configuration here, but all these clusters have very small variance regarding to the excess energy. So they're quite similar. And also we find a single cluster for n equals to 1, 2, and 3, which represents the clusters with higher excess of energy. So in summary, here we propose a cluster guidance strategy based on feature scaling informed by the value of an auxiliary observable, which means we can take the property that any measure that the specialist might say to us. This is important to select these representative samples and take this into account in our loop to find the more representative samples. We use we take 2 major algorithms, traditional algorithms, to build our toolbox, which is the k-means for clustering and the daisy hopping for optimizing the weights. We use several quality measures in order to suggest to the chemist, to the material scientist, which is the correct or the good choice for a number of clusters, number of groups. We know that this selection, the number of clusters, is a very empirical process, but instead of just set up in a random value, we use this score to guess a good initial condition or even the nice condition for the data set we are considering. In this paper, we have considered these 2 samples, these 2 types of materials, as I mentioned before. And in future work, we want to continue to develop these tools, including more clustering methods and also more optimization algorithms. And until now, all the samples that we use for the clustering must have a label. It means all the samples must have the properties provided by the specialist. So in the future, we want to extend this method for a semi-supervised approach in which just a few samples might have this property. So we perform the clustering, but the biasing of the cluster, we use just a few samples that have this property already computed and solved. So that's it. I would like to thank you very much for your attention. If you have any questions,
Okay, there are questions.
and by the way, I'd like to thank Professor Andrea and Professor Meili for organizing this workshop.
You're welcome. And I have a question, a curiosity. So if I understand correctly, in the application that you have was showing with this cluster, the property that you consider was the energy.
Yes, here's the total energy for the space, and here's the excess energy. But you can use any properties for biasing the
Yes, I
properties.
guess, but clearly the energy it's very meaningful for this kind of systems. And so my question was, since you're not a chemist, but these structures are in a way, in a certain way, connected to each other because the cluster can assume the different stable or metastable structures by there is a pathway on the potential energy surface that connects these structures. Okay, so it is possible in some way to make a classification that highlights the connectivity between these structures? Because, for example,
Yes, in particular, in this work, using not only the 55 size and cluster of copper, we studied for different size of clusters, and we detect exactly that. We start from a low temperature, the dynamics, and see how these structures are transitioning between the states.
Okay.
Using it's not the same approach, but also using clustering approach and community detection approach, other methods from computer science, in order to better evaluate the data from the
Thank you. More questions?
Okay, thank you very much.
So you know.
Okay, the next presentation. The next presentation from University of Perugia, Department of Chemistry, Biology, Biotechnology, and he taught about the protein tetraed networks by invariant shape.
Here.
Yeah, already presenting.
Yes.
Go to the presentation. Sorry.
Okay,
It's okay. Here I have to find the view. View. Full screen. Okay.
Okay, thank you, Andrea.
Okay, my presentation is to some degree related to previous one in a sense, because this, I guess that the target is always the same. How to classify in an efficient way complex molecular structures. So let me explain how is the situation here. The motivation, of course, is how to manage, how to identify similarities and common properties when you are facing complex situations which are typical, for example, of biomolecules, which are huge systems. You can have tens of thousands of atoms connected in a complex way. You can have a very complex molecular structure. And the problem, one of the problems with this kind of molecules is to find clear relationships between the structure, the properties, and the function that this molecule have in the cells, in the biosystems. Okay, this is not yet really clear, and one of the ways to do that is accumulate huge amounts of data. Okay, that nowadays are more available than in the past, and process this data and use them, for example, for machine learning applications and things like that. So with this idea here, for this kind of application, one has to represent the molecule, which has a complex 3D structure, in a way which is suitable for build-up data structures that can be used in many different ways. So the most simple representation, and also the most natural one for a molecule, very complex, is to reduce it to a graph, a network, okay, if you prefer, which is a set of nodes plus some rule that allow you to establish links between them, okay? So the nodes can be identified, for example, in the simplest case, with atoms. Okay, you can use the atoms as nodes in your graph, for example, and links can be, in the simplest case, can be chemical bonds. Okay, of course, this choice of nodes and links is too simple to produce any meaningful result because it's nothing more than the normal user chemical structure of the molecule. We want to do more, and so the nodes can be not only atoms but group of atoms, or can also be properties in the sense that I can use as nodes charge distributions, density, to establish points in the structure, and the links can be really any kind of relationship that we can imagine. For example, legal distance is the most simple criterion to establish links. So we can establish a cutoff distance, and below this distance we have a link. If the distance is larger, we do not have a link. And all these possible graphs and networks that we can associate to the molecule, the complex molecule, can be used to build up vectors, for example, to fit neural networks or matrices and things like that. So the key point for us is that in many cases, this kind of representation and structures are not able to get so much information, okay? Because a molecule has a lot of properties in terms of geometry, also local geometry, in terms of interactions between different nodes, which can be physical interaction in the sense of intermolecular forces or things like that. So the idea is to enhance the content of information of molecular networks. And how we can do that? So we can start from a simple idea. We want to use these molecular networks to facilitate the classification of the structures of the molecules according to many different properties. But the idea is that, for example, when you observe an object, this is a very geometric view, which I'm proposing to you. When you observe two objects, in order to establish if they are similar or not, you have to orient them, okay? And you have to look at them from some standpoint from which they appear just identical, okay? This means that you have to rotate, orient, until you can superimpose more or less these two different objects, and you can say that they share a similar feature. Okay, so they are identical with respect to the criterion that we have chosen. Since the idea is to rotate complex structure, we have to look at them in terms of the global shape or maybe local shape. Okay, shape is just the shape of an object, and a shape has to be invariant with respect to the possible rotations and transformations that we can apply to the object. So we want global, local shape parameters, which are also invariant with respect to the operation that we have to perform to identify the similarities. Okay, this can be invariant shape coordinates, and we have to ask ourselves how can we generate these kinds of parameters. And one way to do that is to use the Cartesian coordinates that we can associate to each big molecule, for example, the protein. Okay, this means that we have, for a system of n particles, we have 3n numbers, okay, which are Cartesian coordinates, and we can use them to build a matrix which has sizes 3 times 7, okay, and the columns of this matrix, which is a very long one, it is almost a vector, no? Okay, which is a very long one, are made up by the Cartesian coordinates of each other, scaled by masses. Okay, why do we want to scale by masses? Because we can insert into the coordinates more information. Masses are very important in the sense that you can look at molecules as a distribution of mass also, no? In a sense. So we can map these two properties, which is the position and the mass. Let me put it that way. We can build this matrix, and then we can use orthogonal matrices to act on the zeta coordinate matrix, generating rotated structures, in a sense. We can use two kinds of rotation matrix, which are different by the dimension, because we have two dimensions. We have, of course, three-dimensional rotations, which are physical space rotations. Okay, and they can act from left on this matrix, generating rotated structures. Okay, then we can use a n times n rotation matrix, which is identical, but it is of higher dimension, and this has to act from the right, just for the simple multiplication rule of the matrix. No? Okay, so we can generate different coordinates matrix, and when we do that, we realize that although these are clearly rotations, these are not rotations in physical space. So if we look at rotated structures, we can see that the particle inside switch their position, and for specific choices of the matrix, you can also just change, permutate the position of the particles. Okay, these are known as kinematic rotation. These are ordinary rotation. But the point for us is that we have to apply all this rotation and look at which property of the zeta matrix remains unchanged, basically. Okay. To do that, we can resort to singular decomposition of the matrix, which, by the way, produces a three-matrix product here, where, by chance, but not really by chance, because it has to be so, the two matrices R and K are precisely orthogonal matrices of the type that I was talking about just a few seconds before. And the third matrix, which is in the middle here, it is made up by all zeros, with the possible exception of these three quantities, which are placed in this diagonal of the matrix. And these three quantities are really invariant with respect to all these kinds of rotation. Okay, these quantities are invariant, are also subjected to these inequalities. Okay, and they can be put into relationship with the principal moments of inertia of the system, because we inserted the mass inside the coordinates before. So we can make this association, and this is useful because we can give a physical interpretation of these quantities, which is, of course, related to the shape, okay, of the molecule. Why the shape? Because these quantities are connected to the spherical oblate or prolate character of the molecule. Okay, so if we have three sides equal, we have a sphere in the sense of rotational symmetry. If we have this situation here, we have an oblate top, which is this one, or this shaped structure. And if we have this condition, we have a prolate cigarette structure. Okay, So we can also build deformation indexes that measure, in a sense, the distance of the shape from the perfect spherical ones. Okay, these are really deformation. And we can also calculate this cumulative index, rho square, which is a measure of the size of the system. Okay, and so now another little step forward, and we have to consider the special case when the matrix of the coordinates is square, which is just the product that is very crucial, very important for atom or for center system case. Okay, why, if you have 4 atoms in general, you can separate the center of mass. So you really need 3 vectors. This means that you have 3 times 3 matrix, and this is a very simple case. And what you see is that you have a 3 times 3 matrix containing these quantities, this size, and the volume that the system occupies in the physical space. It can be shown that can be obtained just as the determinant of this matrix, okay, which is, by the way, for a simple, if you fix, in a sense, this matrix, okay, you can just obtain it as the product of these 3 sequences, okay? This means that the sign of the smaller psi determines the sign of the volume, which means that you can distinguish between the chirality sign of the geometrical shape. Okay? Okay, let me stop here to accelerate, and let me just show what is the idea. The idea is that we can reduce the complex structure of a protein to a sequence of tetrahedral centers, okay? Because each amino acid in the sequence, it is really physically just based on a carbon atom surrounded by 4 centers, okay? So we can imagine that a complex molecular structure like that of a protein it is a sequence, a chain of tetrahedra, okay? For each tetrahedra, we can generate size, we can calculate the size, and the 2 deformation indexes. So from one single structure, we obtain a lot of size for each of the centers, okay? And let's see what happens, for example, and this is the illustration of what I was telling you here. We have n times 3 size for each protein structure, okay? And what is the first kind of application we can think about? Many of you know, or you met sometime in your life, is Ramachandran plots, which are just the distribution, the scatter plot of the angles, physical angles that you can collect from the structure of the molecule, the protein. Okay, and why it is important? This kind of it is a kind of existence region plots. If you find that the proteins lies outside these areas, the populated areas, the conclusion is that probably the structure has been measured in a bad way, so there is something wrong. You can think to do the same, more or less, using the size. This is the first most simple application you can make. And here I show 500 structures, protein structures from the PDB protein data bank, which are publicly available. And we can extract for each molecular networks. We have 500 tetrahedral networks from these structures, and we can calculate the distribution of the size. These are the 3 possible plots, and we can also see that we can merge them in this way. And you can see that the result is that you can find some kind of existence regions too, and there are some nice features here that I have still to interpret correctly in terms of geometry of the structure. And this is a first kind of application. Just second kind of application, it is related to specific amino acids in the protein structures. Okay, you can ask, for example, which is the situation for a particular amino acid, glycine, for example, proline or alanine, which are the most common ones, present one in general in the structures. And you can do, for example, this by analyzing specific structures. I'm going to show you what happens. For example, for 1A0 and 1A03 proteins, you can just plot the glycine, proline, alanine deformation indexes. And this is one result. This is another result. As you see, the distribution is similar, very similar. This is a very small protein, so we have not so much data, but here too we have similar distribution in for this scatter plot, and we can do that cumulatively for all the set that we were using before, and you can observe that it is really a kind of fingerprint for these three amino acids. Okay, so this is a very good way to test the protein structure in the sense that normally these three amino acids should lie in this region, okay, exactly. And the same happens if you do similar calculations for the size. You obtain these fingerprints for the glycroala to be scatter plots. Okay, I think I can stop here. These are just exemplary applications. Let me draw some conclusions. So this invariant shape coordinates can be used to generate networks that can be associated to each protein structure. Okay, this kind of indexes indeed have a high information content because they measure the local deformation of the amino acids, and this deformation can be in connection with also interaction in perspective, okay, because that must be due to interaction, tension in the structure, and so on. And this same approach can be applied to different kinds of molecules, for example, DNA. Okay, this kind of data collection and plotting can be done in a systematic way, and one can try to find association between specific structures of characteristic of the local structure of proteins, for example, beta sheets, alpha helix, okay, that can be associated with specific values of indexes. And also there is the possibility to connect this size to the chirality, the local chirality content of the chiral center, because these are here chiral units, so you can generate a kind of measure of the degree of chirality, okay, of each center, and it is an additional information that you can use to enhance the content of the network, okay? And I can stop here. Thank you for your attention.
Okay, the paper is now open for the discussion. If there is some question.
Have you considered using any type of graph neural networks to extract invariant features that and
yes.
compare to your approach?
I want to do that in immediate future. because it is precisely the initial idea was to generate a way to feed neural networks.
But I mean, if you take a graph, neural networks into account, you can take the raw graph, the molecule, even with the properties assigned to each node connection, and feed in neural network with the whole raw data. I think it would be an interesting approach to compare.
Yeah, definitely. Okay.
A curiosity, from a computational point of view, how long are these calculations?
It's no, it's just instantaneous. In the
Instantaneous.
sense that it's just to, once you collect all the data on the structures, then to extract these quantities, it's not computationally demanding. Because here, in practice, it is based on the 3 times mathematics diagonal division, which is can be analytic.
Okay,
Okay, so it's
thank you.
so the last
So the
presentation
last
not
one
going to
is
be-
not
because
going to be
they-
presented. So now we have to end the
maybe the
the session.
Yes,
Thank you,
thank you.
all of you. So next session begins at this room after coffee break. Yes, you can have your coffee.
Okay.
Did it happen something to your Gmail account? Because when you tried to open it here,
no,
he asked to
he asked
reset
for security.
for
because
security
Each
reasons.
time I connect from unknown IP.
Yes, from here. I know I have Gmail too. And okay, everything's okay.
Nice to meet you. Thanks for the session.
Congratulations for your. I am an engineer and I'm in urban planning. So these are a little bit strange for me. But I know the tetrahedral and all those geometrical.
I am the next.
The next, yes, of course.
Yes, Marcio
Of course,
Rossi.
of course.
For the presentation, I have to put the presentation because I am actually for the next session. I am the only one in presence. The other 2 are online. So
Espera que yo ponga bien esto. La otra sí es aquí.
Let me check here. So you are the first.
the first one.
Okay.
Yes. While the second one actually is not in presence but is virtual
Okay.
because it's Marco Pagliani
Okay.
presenting and
Virtual.
virtual and also Luca Mancini.
In virtual, it was as scheduled. Scheduled virtual.
Yeah.
It's the same. It remains.
Yes.
Thank you.
But this is, I think that this is an error because he was supposed, also Marco Pagliani, to be virtual.
Okay.
So there is only that presentation because
It's in a PowerPoint.
the PowerPoint. Yes.
Okay, I will translate it in PDF because there is a problem with the PowerPoint. I will show you. Not a problem. I mean, here, if I open this, when I open this, I have to activate. So skip it for now. Not this. If I do it in a presentation mode, the rooms from the virtual rooms cannot see. So we have 2 options. First option is to open with Libre PowerPoint,
Okay.
but Libre PowerPoint change a little bit. You want to check what's
No,
going?
we can try with
We
PDF.
can do it in PDF.
Let's
Okay.
see, but I think that it should be okay, PDF.
Okay.
amigo que decide cuál es los grupos de alumnos que quieren ver.
Yo pienso, yo creo que a presentar, pero yo pienso que va a pasar.
Let's see.
Claro, y deja resultado. Ahora esperamos.
It's okay.
No, que se mandé a hacerse. Que no tenía la presentación la que hago.
Perfect. Just a moment.
We can leave the things here.
Yes, I will be here.
Okay, perfect. El teléfono andiamo. Claro, ¿quién lo va a
Okay, thank you.
Noi lasciamo tutto. Ok.
Okay, see you again later. Thank you.
morning.
How are you?
How are you? Fine. How is your time?
Very satisfying.
Okay.
Both at the
Pleasant.
conference. Yeah, pleasant. Both at the conference and around this.
Perfect. Enjoy. We have coffee break now. Niente, hanno spulito nel virtual sull'aspetto. Lei sta avanti. Ah, bravo. Guardati sullo stesso ora di Caterina. Ok. Allora. O ti fez? Eu vou mais um pouco no três ou três elementos mi insegnarà tendenze. Non è possibile, ora si sbagliare, userò un formato di da questo parte da un docente non buono, da no, sport, stelpa, i to będzie nasz sport, a fizyka ofert etyka. I tak se hasi, kako fizyki na mene, etyka ili kriti. Ne. Αλλά δεν έχουμε χρόνο, θα πάμε Δευτέρα και γυρίσουμε Τρίτη. Αυτό είπα, ναι. Να δούμε τι θα αφήσουμε τα παιδιά. Καλά, θα δούμε. Μπορούσε ο Θάνος, μπορούσε να πει στα παιδιά, με τη παιδιά, και να μην το φέρει στο δημόσιο πρόσθεση στα συναγάλια. Πειράζει. Αυτό τα σκέφτηκα και την εννοεί μου βλέπουμε την κάνω. Είναι στην ίδια που δεν θα μπορούμε. Εντάξει. Άντε, ναι. Περιμένω να πω τι κάνεις. Δεν είμαι και πολύ καλά. Γιατί έχω πάρει κάτι σοβαρό, θα σου πω όταν έρθεις. Ναι, αν ξέρεις τι είναι. Θα είναι μέχρι τις 5:30 θα έρθει. Εντάξει. Ναι, να μπορώ. Η Δανέια θα πάει στις 3. Ο υδραυλικός θα πάει, δεν πήγε, ήξερε το 2 βλέπουμε. Ο υδραυλικός 2 με 4, γι' αυτό της είπα να πάει 3. Μήπως θα βολεύσει και τον υδραυλικό, να κάτσει να τον περιμένει. Ναι. Καλά, εντάξει, είναι βλάκες. Το master bedroom δεν σου είχε πει. Αυτό και δεν μας ενδιαφέρει. Ναι, εντάξει, αλλά εγώ νόμιζα δεν έχει το άπλωκα. Το να μην τρέχει καλά, το να μην έχει κρύο νερό, έχει μεγάλη διαφορά. Το που δεν έχει κρύο νερό, παιδί μου, αυτό ήταν το πρόβλημά του. Και γιατί φέρνουμε τώρα τον υδραυλικό. Αυτό το ξέραμε. Λουκά, μπορείς να μου μεταφέρεις την πληροφορία. Ζεστό νερό ή κρύο. Ναι. Και έχουμε πρόβλημα και στο μικρό μπάνιο. Περίμενε τώρα. Ο υδραυλικό, καλά. Άμα είναι να πάει ο υδραυλικός χρήση ώρα, να πω, να ελέγξει και τα ελέγχει και αν είναι να φτιάξει κάτι, αν μπορεί τώρα, γιατί δεν μάθει τη Δευτέρα της άλλης στιγμής. Εντάξει. Γιατί εσύ εγώ δεν σου πήγα καθόλου κρύο. Λουκά, μη φωνάζεις, μεταφέρεις όλα τώρα μου, αλλά αυτό που θα αλλά πρέπει να μου τα λες και εμένα. Πρέπει να μου το λες και εμένα για να το λέω στον άνθρωπο. Ωραία, πες στους 3. Μια χαρά είναι η σύνδεση. Αλλά θα στο δείξω εγώ, ναι, εντάξει. Και έτσι ούτε στο τηλέφωνο και μου. Ναι. Αλλά εντάξει, να σου πω κάτι, πες στους Ιταλούς, 3 η ώρα είναι εκεί να έχουν το κλειδί απ' έξω. Και από τη στιγμή που θα πάνε σήμερα οι καθαριστές, θα πάνε και αύριο. Δεν πήγαμε έτσι. Λουκά, προσαρμοζόμαστε. Από τη στιγμή που συμβαίνουν έφεκτα, προσαρμοζόμαστε. Ρωτάω να το συναντηθείς. Θέλουν εκεί στις 3 να τους πούμε ακριβώς τι θέλουν να κάνουν, να ησυχάσουμε. Να μην μας κάνουν συνέχεια παράπονα ότι δεν είναι ευχαριστημένοι. Γιατί δεν είναι εκεί να τους πούμε τι θέλουν. Ωραία. Μπορείς να τους πεις ότι στις 3 θα είναι η καθαρίστρια, μπορείτε να είναι κάποιος, τι θέλετε να κάνει καθαρίστρια. Μπράβο, τι θέλετε να κάνει καθαρίστρια. Και αν δεν είστε εκεί, να αφήσετε κλειδί. Και στις 3 θα έρθει και τηλεφωνικός, έτσι. Καλημέρα και συγγνώμη για την ενόχληση. Είναι ακριβή. Ήθελα μόνο να πω το εξής, ότι γύρω στις 3 θα είναι εκεί και καθαρίστρια. Που δεν είναι καλό να σας δείξει τι γίνεται. Θέλω να πω μην πάτε νωρίτερα αν σας βγει. Δηλαδή μετά τις 3 με 4,5 θα είναι σίγουρα. Ναι, τέλεια. Εντάξει, θα το πω. Ναι. Ναι, τέλεια, εντάξει. Ευχαριστώ πάρα πολύ, ευχαριστώ. Ναι. Benissimo. Έλα μου τι κάνεις. Να σου πω, 3 η ώρα θα είναι εκεί και ο υδραυλικός, μου είπε, για να του δείξει αυτά τα 2 μπανάκια, και αν μπορεί να κάνει κάτι. Να σου πω την αλήθεια, μου είπε ότι θα έρθει από άλλη δουλειά, αλλά δεν τον ρώτησα αν είναι να φύγεις μαζί του. Ναι, ναι. Οπότε μου είπε, στο τέλος πάντων, εγώ τους είπα, δύο λεπτά μιλάμε τους Ιταλούς, για να μην μας αρέσουν τα πάλι, τι ακριβώς θέλουμε. Πέρα, ας πούμε, ότι θα πρέπει να καθαρίσουν κάτι και τόσο και ξέρω άλλες αυτές, τι ακριβώς θέλουμε εκτός από τα μπάνια. Α, πήγε. Ωραία, οκ. Α, και τον έστειλες. Εντάξει. Εντάξει. Όχι, εντάξει. Τι λες τώρα. Εντάξει, καλά δεν είναι, οκ. Ναι, ναι, ναι. Ωραία. Καλά, πήγαινε να σου πω πάρε και χλωρίνες, γιατί δεν ξέρω πόσο έχουμε. Α, εντάξει. Εντάξει. Οκ. Εντάξει. Εντάξει. Και θα ξαναμιλήσουμε. Έλα, σε ευχαριστώ. Γεια. Έλα, Ναταλία.
Δεν κάνω τελικά το βράδυ.
Όχι, ξέρω.
Γιατί έμαθα ότι θέλει να με βάλει diverse εθνικές. Δηλαδή, με έχει φέρει στο σπίτι να τους μαζεύω αυτούς. Να πω ότι έχω άλλο τρόπο να πάω.
Πες το πάμε άλλο τρόπο.
Και τελικά να πάτε εσείς τα κάνω.
Θα πεις ότι ο άλλος εδώ δεν θα έρθει και αυτός ήμουν εγώ. Γιατί αυτό το άλλο το πάω όταν αν το μάθω. Εντάξει, μην το αναφέρεις, πες τα με έναν άλλο τρόπο. Και πες που κάνουμε συνέχεια με έναν άλλο τρόπο, μπορεί να το κάνει κάποιος άλλος. Δεν θα σου πω. Εντάξει.
Of course.
Okay.
se riesce a seguire da remoto, immagino siano collegati sui perché tu sei il primo, no? Sì. Quindi ti introduco io, poi dopo se come vuoi. Poi dopo vai avanti tu, insomma. Sì, io ho provato con la sessione funzionava beh, formalmente ti introduco io, che fa piacere. No, beh, Marco, no, dopo fai tu. No, fai tu perché, anche per Marco c'è. C'era tutto. Luca, tutto bene? Sì. Sì, adesso alla fine c'è facciamo dopo, conoscevo magari lo consideravo pericoloso. Mi era sì, io questo sono risultato così, seguo, no? Cioè, non è che l'ha tagliato il titolo è che questo va tagliato. È questo, perché qualche volta non tagliamo, anche perché questa è già tagliata. Sì, facciamo, prendiamo l'autobus. Lo andiamo a prendere lì e fuori, quindi vabbè, la
Salve signori.
Salve Marzio.
Ma Marzio ti sei visto? Sei sul video del secondo giorno di ieri dell'ICCSA alla sera, non ti sei visto su Instagram? Dopo ti faccio.
Ma per sera?
È il video di tutto il giorno finito con la sera. Ma dopo se tu vedi il post, il video che hanno fatto, sembra gigante il post di ieri sera. Sembra che pensa tu.
Ma io parlo di questo, sempre sera.
Sì, sei tutto sorridente lì con i tuoi colleghi. Tiene la mochila. Ok. Las cosas, esto lo quieres, el experimentes. Allora, come c'è? Se lo podía haber dicho al tío agua. Perché antes cuando yo hablaba, si querías que te pusieras una historia. Va bene. Un poco discreto, ¿no? ¿Quién es? A ver, Alicia, di noche. Agustín. Espera. Aladino, Alibaba, Blancanieves, Blancanieves, Capuchinoso, Sì.
Can you put this in the
The
computer?
second presentation?
Yeah.
Ah, no, it's for your convenience.
Yes, just to use this to change the slide.
Okay.
Yeah.
Bianca.
Indietro.
Es el puntador. El menor que vino. Ah, puede ser, sí. Puede ser. Sì,
Yes, for the first presentation.
Oh,
Just only for that.
perfect.
Yes.
Just joking.
Then we will pass the rose to
Okay.
the chairman. Yes. Luca è collegato.
È l'ultimo.
Luca è collegato.
Ah, perché di non che scrivevamo che non c'era. Secondo me la caricata così grande. Io che ne so, le di notte.
sì, quale?
Eh sì, che deve essere abituale. Non lo so, io è italiano, ma non lo so, non so.
Sì.
Welcome to the section of Compastro workshop. Let me introduce you Professor Marzio Rosi, which is the first speaker of this section. The co-authors are of the first presentation titled A Computational Study of the Reaction Between Nitrogen Double D Atoms and Simple Aromatic Hydrocarbons. The co-authors are Nadia Balucani, Pier Giorgio Casavecchia, Noelia Faginas Lago, Luca Mancini, and Dimitris Kouteris. Please, Marzio.
Just a moment. Entire window. Why? Okay. You're right. Thank you so much. And just 1 second. Give me. Okay.
Okay, thank you very much. First of all, I would like to thank the organizers of ICCSA 2023 for giving me the opportunity to present my work and also the opportunity to be in the Athens, which is a really beautiful city. This study is a joint research between a group of theoreticians and a group of experimentalists, both from the University of Perugia. Okay, perfect. We are interested in the formation of organic molecules containing nitrogen, because the synthesis of nitrogen containing organic molecules is a crucial step in prebiotic chemistry, as they are potential for important biological molecules such as amino acids. In this context, the interaction of nitrogen in its perfect cycle double D state with small hydrocarbons is particularly interesting, because nitrogen in this state is particularly reactive. Interestingly, simple species beyond both nitrile and immunophages have been detected in the interstellar medium and in the upper atmosphere of Titan. The Titan is the largest moon of Saturn, and it's particularly interesting since its atmosphere is believed to be somewhat reminiscent of the primordial atmosphere of Earth. Indeed, the atmosphere of Titan is composed mainly by nitrogen, which actually is almost 97%, and small hydrocarbons, in particular methane, but also aromatic hydrocarbons like benzene and The temperature at the surface in the atmosphere of Titan is very low, so only reactions which do not present an entrance barrier can be considered. Molecular nitrogen, we know that it is a very stable molecule and is almost unreactive. However, in the atmosphere of Titan, it's possible that due to the energy provided by sunlight or energetic particles, we have dissociation of molecular nitrogen in formation of atomic nitrogen, of course, in its ground state, for S ground state, but also in exile states, in particular the WB state, which is very reactive. Atomic nitrogen in the WB state can react then with methane or other small hydrocarbons, and it can give rise to more complex organic molecules, and at the end they can give rise to tonic, that is complex organic molecules with very high molecular mass. We have already investigated the reaction of nitrogen WB with several aliphatic hydrocarbons, and these both theoretical calculations and performing cross-molecular beam experiments. With the same approach, now we want to study the reaction of nitrogen WB with aromatic hydrocarbons, starting from the simplest species like benzene and toluene. But the goal is to arrive to study also complex aromatic hydrocarbons like polycyclic aromatic hydrocarbons. In the scheme of our investigation is here reported. We consider experimental information, in particular the experiment can provide information about the primary products of the reactions, the investigated reactions, and the branching fractions. Using theory, we can compute the potential intersurface of the system of interest, and then we can use energies and frequencies to perform statistical RKM calculations in order to get theoretical branching fractions. We can use then this information to compute the rate coefficients, which can be included in the models of astrochemistry, in order to have correct interpretation of astronomical data. Here is the scheme of the experimental apparatus, where there is an atomic beam source, in this case nitrogen WB, and a molecular beam source, in this case benzene and toluene. And while the theoretical calculations are performed using UFT theory to evaluate the potential surface, in particular to optimize the geometry of lima and transition states. First, we use a small basis set to have a first scan of the surface, then we refine the calculations with beta basis sets. The stationary points then are computed at higher level of accuracy, in particular couple cluster, with inclusion of single, double, and triple excitations perturbatively, and at the end to reach the so-called chemical accuracy of the is an error smaller than 1 kilocalories per mole, we perform an extrapolation on the basic set and include also covariance correlation effects. The critical point of the interaction naturally with small aromatic hydrocarbons is the formation of the initial adduct, which is an electrostatic adduct where the nitrogen actually is very far away from the ring, the aromatic ring. The interaction so is very weak. The computation of the geometry, of the optimized geometries, seems to be reasonable, but what is clearly wrong is the evaluation of the energies of this initial point. This is the adduct for N plus benzene. This is the transition state of this adduct to the first stable intermediate. And this is the same for toluene, initial adduct and transition state. The energies are reported CFT, couple class, and CDS level. And in any case, at any level, you can notice that there is a clear overestimation of the interaction energy for this gas. This is not a reasonable value because this interaction is very. Why there is this error? Because here the nitrogen is still in its exact double state, and this system can be described properly by a single reference method. It's necessarily a multi-reference method. However, this point is not so critical because all the reactive channels start from the first stable intermediate. So we can start considering the first stable intermediate and have information about the reactive channels. The potential energy surface is very complex. This is only a part of the potential energy surface. It's very complex. Indeed, we have under the reactants, so possible channels, possible reactive channels. We have for this system a minima, stable intermediates, and connected by 25 transition states, and we have 10 exit channels. In order to understand better which are the reactive channels really important, we perform using the couple cluster energies, arrive KM calculations, and evaluate complete the branching fractions. And then we focus our attention only to the channels which show value of the branching fraction higher than 1%. So we are able in this way to select the reactive channels and we can see that the most important exit channel is this one, the one leading to the formation of hydrogen channel. This surface computed CDS level, that is completely set in conclusion covariance correlation. For toluene, of course, the situation is even more complex because the presence of the multiplied group drop very symmetry. So we have the possibility of more isomers. Here is only a preliminary study of the surface of nitrogen WT and interacting with toluene. However, since we are interested in particular in the computational requirements, we can select also for N-toluene the exit channel, which is the most stable compound, that is the channel leading to the formation of hydrogen channelized, and compare the methods employed. Let's start with N+benzene. Here we have selected the exit channel leading to HCN. Actually, there are two different pathways leading to these products. The one going through intermediate W2 and the other going to intermediate W3. Here we have reported for these two channels the energies computed at DFT, couple cluster, and CDS level. Of course, the turbulent value is the most accurate. You can notice that there are differences between couple cluster and CDS energies, which can be even larger than 5 kilocalories per mole. So even accurate calculations like a couple cluster with a triple zeta clusterization basis set provide results with an error which should be taken into account. We can notice also that actually the DFT values are most of the times very close to the CDS results. Of course, this is due to error, cancellation of errors. However, this suggests that at least for semi-quantitative calculations, the FFT calculations are still a good compromise and maybe can be used for larger systems like interaction of nitrogen, WD, and polycyclic aromatic hydrocarbons, where other approaches are unfeasible. There are situations similar or for N plus N WD plus toluene. Here we selected the same exit channel. Of course, the other channel seen for benzene, since toluene has this methyl group, in this case leads to different products, to the formation of methionine. But here we still do the CDS calculations, and we can notice between DFT and couple cluster values difference which cannot be considered small, very small, and but the computation performed for benzene actually suggests that probably the correct value is not a couple cluster result, but are the DFT values for cancellation of error. Okay, so let's reach our conclusions. Our study suggests that we have no problems for geometry optimization, even low-level calculations are adequate for geometry optimization. But for energies, if we want very accurate results, it's necessary to perform calculation of higher level, and even couple class calculations sometimes are not enough accurate. The initial approach of the nitrogen in its double state to the aromatic system is particularly challenging, and this point should be investigated further using multi-reference methods, which however can be difficult to apply to large systems, or maybe considering other approaches like, for instance, symmetrical methods include like it include Raymer-Jones calculations which Noelia previously presented. I can conclude. Thank you for your kind attention.
Thank you, Marcel, for the very interesting talk. There is time for questions. Please. I have a curiosity.
Yes.
In Titan atmosphere, is it possible also to have reactions between N plus ions and the molecules?
Yes, if you have ions, indeed the reactions are possible because usually the ions we do not have an entrance barrier for the reactions. So what we can exclude is the possibility of reactions with entrance barriers, even small entrance barrier, because the energy for the reaction is only the initial energy of the reactants. So you cannot overcome an activation barrier. But for others, the reactions are surely possible.
Thanks.
I have a more questions. How do you do the complete basis evaluation?
Yes, we perform the complete basis set, making extrapolation of couple of level using double, triple, and quadruple class polarization. And we use there are many extrapolation algorithms. We use the one tried by Martin, Jan Martin, which was published several years ago. So we perform calculations, extrapolating the computer set in this way, and then we add those or the covariance correlation effect, which in order to get very accurate results, it seems to be also important.
Somebody has a computational cost.
Yeah, it's very high. I mean, for N plus benzene, to perform a work at this level, we compute only the energy, not the kind of the optimized
single point.
the single point calculation. And for N plus benzene, single point calculations require in our cluster several days of computation. So that's the reason why we haven't yet finished the same calculations on N factorial, because the system is larger and less symmetry, and so a lot of problems.
No more questions? If not, thank you again.
The next speaker is Marco Pagliani. Marco Pagliani, which is connected from remote, is not connected.
Maybe we can skip to the next presentation and then wait for.
Yes, I can see that the next, the other speaker, Rancini, is connected. Maybe we can speak to the other speaker. Rancini, good morning, Luca.
Good morning.
Okay, can we ask? And we will be back to Marco after the Rancini. And Luca Mancini will present computational study titled Computational Investigation of the nitrogen WD with ethylene and CH2, CHCN reactions. Okay. In variational analysis implications of Titan atmosphere. Luca, you can start.
Okay. Thank you for the introduction and for having me here. I hope you can hear me well. As already introduced, my work is related to the computational investigation of the reaction of atomic nitrogen in its electronically excited state WD with different hydrocarbons, ethylene and acrylonitrile, with possible implications for Titan's atmosphere. As already introduced by the previous talk by Professor Rossi, we are interested in Titan basically because of its potential prebiotic role. Titan is Saturn's largest moon. It's the second largest moon in our solar system, and it's the only body except our planet to have a thick atmosphere mainly composed by molecular nitrogen. And this leads to this body to have a strong prebiotic potential because the appearance of life on our planet strongly modified its geomorphology. So in order to reconstruct the first evolutionary stages of the prebiotic chemistry that possibly ultimately led to the emergence of life on Earth, we have to look at other bodies. And the best candidate is Titan. For this reason, different missions have been performed, starting from the Voyager mission up to the last fascinating Cassini-Huygens mission, which was actually able to land on Titan's surface, and we have plenty of data about the structure and the composition of this body. According to the last model, Titan is composed by different layers, also including water ice layers, and the outer one, which gives this orange peculiar color, is composed mainly by hydrocarbon. As said in the previous presentation, the temperature in the surface is around 94 Kelvin, which means that all the water is present as water ice, and there are liquid, mainly methane, but also ethane, which fills river, lakes, and also a cycle which is similar to the water cycle on Earth. While the atmosphere is mainly composed by molecular nitrogen with a small fraction of methane and other carbon-rich compounds. Here I report the plot of the temperature and pressure as a function of the altitude, and we can see that the increase of the altitude leads to a decrease of pressure and temperature, and in particular at around 1,000 kilometers of altitude, so in the upper atmosphere of Titan, the temperature is around 180 Kelvin, and the pressure is 10 to the minus 6 millibar, which in principle will lead to conditions which are prohibitive for molecular growth. But the missions and the ground-based observations revealed the presence of complex molecules with dimension going up to 8,000 Dalton. So with the C and H ratio close to 1:1, leading to an active and complex chemistry taking place, driven mainly by nitrogen. Finally, we are all waiting for the new NASA mission Dragonfly, which is scheduled for the next year and will give us new information about this body. So in this work, I studied the reaction of atomic nitrogen with two molecules, ethylene and acrylonitrile, which both have been detected in the upper atmosphere of Titan via ground-based observation, also through the ALMA interferometer and via space mission. And if we look at the abundance of this species as a function of the altitude, we can see that the mole fraction shows a peak at around 1,000 kilometers of altitude. And at the same altitude, also the abundance, the mole fraction of NWT is very high. So also if we take into account the mole fraction, these reactions are possible and feasible in Titan's atmosphere. As we said before, the main component of Titan's atmosphere is molecular nitrogen, which is characterized by a high chemical stability. So the main actors that drives the chemistry in Titan's atmosphere are the so-called active nitrogen form, which are nitrogen ions, nitrogen radicals, and atoms. And in particular, the interaction of N2 with extreme ultraviolet photons and other energetic particles, including also Saturn magnetospheric electrons, lead to the formation of atomic nitrogen in both the ground state 4s and the first electronic excited state WT. But unfortunately, the ground state is not reactive with closed shell molecules, so the main reactant partner is NWT, which is characterized by a long radiative lifetime and a high energy content of around 230 kJ per mole, leading to a very high reactivity of this species. In this work, I performed a theoretical analysis of the two reactions of NWT with ethylene and acrylonitrile, which can be seen as an ethylene molecule with a nitrogen atom substituted by a CN group. So we want also to understand if the presence of the CN leads to a different reaction mechanism. We performed the first analysis of the potential energy surface at the TFT level with the triple zeta basis set to optimize the geometry of all the stationary points and to calculate the harmonic vibrational frequencies in order to check the nature of the stationary point. The geometry optimized at the TFT level has been used to compute the energy with the more accurate coupled cluster CCSDT level with the same basis set to obtain a more accurate energy values. And we performed also more accurate calculations at the coupled cluster level with the extrapolation of the complete basis set with correction for core valence correlation effect. And these values has been used as a reference to check the goodness of the other coupled cluster calculations. I can show some results. This is the potential energy surface for the reaction of NWT with ethylene. As we can see, the reaction starts with the barrierless attack of atomic nitrogen to the carbon-carbon double bond of ethylene, leading to the formation of a cyclic intermediate, min1, which is characterized by the presence of a CNC group. And once formed, this minimum can directly dissociate to hydrogen displacement process, leading to the formation of the cyclic CH2 and CH fragment. Or alternatively, it can isomerize to form a linear intermediate through the breaking of a carbon-carbon bond, followed by a hydrogen displacement process. In this case, we located a transition state whose energy is the same as the energy of the product. So in principle, we can also remove this point from the surface, but we included it because it helps the kinetic investigation, because the final aim of the theoretical investigation is to obtain a complete potential energy surface to be used in kinetic calculation to derive rate constant and branching ratios, which are the parameters needed for the photochemical models of Titan. We can see from the analysis that the reaction is barrierless, and all the stationary points lie below the reactant energy asymptote. So the process is globally exothermic, and together with the absence of an initial barrier, we can say that the reaction is feasible also under the low temperature and pressures conditions of Titan. The same approach has been used to derive the potential energy surface for the reaction with acrylonitrile. We can see that the mechanism is more or less the same. The only difference is that the potential energy surface is a bit more complex, and this is due to the fact that the CN group removes the symmetry of the ethylene molecule and opens up new possible product channel. But also in this case, the first step is the barrierless attack to the carbon-carbon double bond, leading to the formation of the cyclic intermediate, which can directly dissociate and form atomic hydrogen, in this case with two possible cyclic cofragments, depending on which carbon-hydrogen bond undergoes fission. Alternatively, also in this case, through a transition state, MIN1 can isomerize to the linear intermediate, which can directly dissociate to form atomic hydrogen and linear cofragments. Here I report the energy that we for the different stationary points that we obtain at the coupled cluster level with the triple zeta basis set and with the extrapolation to the complete basis set. I reported the energy in terms of relative differences of energy between the stationary points and barrier heights. And we can see that the differences are very small, especially if we consider the relative energies. So in principle, even if the CBS extrapolation is the best way to obtain accurate value of energy, in principle, we can use also the triple zeta basis set to obtain reliable data to be used in the kinetic analysis. So a first analysis of the potential energy surface can lead to the conclusion that the only effect of the CN group is the removal of the symmetry of the ethylene molecule, and therefore we obtain a more complex potential energy surface. But a complete investigation of the potential energy surface led to another result, which is somewhat surprisingly, and this is due to a new possible reaction mechanism. And the reaction mechanism depends on the high energy content of the NWT. So in general, the mechanism of the reaction of NWT with hydrocarbons depend on the partner molecules. And for unsaturated species, we mainly have the attack of NWT to the carbon-carbon double bond or triple bond, in general to the pi system of the molecule. While in the case of saturated species, the main reaction mechanism is related to the insertion of NWT in a CH bond. But in the case of nitrile molecules, we noticed that the high energy content of NWT lead to a new possible reaction mechanism, which is related to the attack of atomic nitrogen to the nitrogen side of the nitrile molecule, both to the nitrogen lone pair and also to the CN triple bond, which is usually characterized by a high stability, and that's why we were initially surprised by this possible attack, which leads ultimately to the formation of molecular nitrogen. So we performed a full investigation of the potential energy surface, which is extremely complex, but we can say that the nitrogen side attack is characterized by the presence of barriers, also submerged, but are still present small barrier in the entrance channel. And this reduces the reactive flux. So the main attack is the attack to the carbon-carbon double bond and is barrierless, while the other attack we believe is less favorable. Finally, we compared also our theoretical investigation with the laboratory experiment performed in the Department of Chemistry of Perugia through the cross-molecular beam techniques already explained by Professor Rosi, and we showed a very good agreement between theoretical predictions and the experimental analysis. So in conclusion, the theoretical investigation of the two reactions led to shows the same mechanism for the primary attack. So in principle, the primary attack is not affected by the presence of a CN group, but the high energy content of NWT allows also this new attack to the nitrogen side of the molecule, which is still less favorable, especially at low temperature, but it can become important if the temperature increases for other application and not for Titan's atmosphere. We performed a theoretical investigation and we saw that, of course, the best computational strategy is the use of a DFT method for geometry optimization, followed by a coupled cluster analysis of the energy at the CBS level. But it is also very time consuming, so we can say that also the use of a triple zeta basis set with coupled cluster calculation can provide useful information, and it's the best compromise between chemical accuracy and computational cost. So the future main perspective are the full characterization of the kinetic of the two reactions and inclusions in the models of Titan's atmosphere. Thank you for your attention.
Thank you, Luca, for this nice presentation. We have time for discussion, questions. I just I'm curiosity, Luca. So how relevant do you think is the attack of nitrogen to the nitrogen of the molecule? Do you think that for similar systems necessary always to consider also this attack, or is not so relevant?
Yeah, I think it's relevant. I mean, just for completeness, for sure. And but if the results are the same of this analysis, so if for also other nitriles there is the presence of this submerged barrier, I think that for our purpose, so to model Titan's atmosphere, this attack is less important than the other one. But of course, it needs to be fully understood and analyzed.
Okay, thank you. Thank you, Luca.
Thank you.
Other curiosity? Okay, so there is no other questions. We can thank again and we can go back to Marco Pagliani, which now is connected.
Yeah.
Good morning, Marco.
Can you hear me?
Yes. Perfect.
Okay. Sorry for me being late, but I didn't take into account the hour delay between Sweden and Greece. Sorry.
No problem. We just changed the schedule, and so we are perfectly on time. We are
Okay.
not late. So Marco Pagliani from the University of Perugia will make a presentation on the fermentation dynamics of chemical molecules induced by ultraviolet and ultraviolet photons. You can start when you want.
Okay. Good morning, everybody. My name is Marco Pariani. I am a PhD student at the Department of Civil and Environmental Engineering at the University of Perugia. And my current line of work is on double photoionization of small gaseous molecules, which can be of potential environmental and astrochemical importance. So today I will present a work which name is Fragmentation Dynamics of astrochemical molecules induced by UV and UV photons. And in particular, I will present some preliminary data about the double photoionization of alene. In the first place, why are we interested in studying ions? Well, we all know what an ion is. It's an atom or a group of atoms that carries positive or negative electric charge as a result of having lost or gained one or more electrons. Now, in our group, we are mainly focused on doubly positive charged ions, which are also called dications. But in general, ions have been predicted to exist in the ionospheres of many planets, as well in comet tails, and in general, all around the interstellar medium. And they are of extreme importance because when a molecule or an atom is in an ionized state, it's kind of eager to react in various forms. So it can dissociate, it can fragmentate, associate, and overall it can take part to a series of reactions leading to the formation of some very important intermediates and molecules, such, for example, as CO2, molecular hydrogen, or even water. And of course, the production of these species in space can be really easy thanks to the energetic radiation coming from stars or quasars. As an example, on the right, in the top right corner, is shown a picture from Hubble highlighting some quasars, and you can see clearly some green filaments, which are in fact ionized oxygen, which glows green when ionized. Another great example is H3+, which is one of the most abundant ions in the universe, and its role in the gas phase chemistry is unparalleled by any other molecular ion, and is involved in many reaction pathways. In particular, its destruction can lead to the formation of HCO+, OH+, H2, and also to water in traces. We might say that, generally speaking, studying these species and processes can be of great interest, also to investigate some of the prebiotic chemistry on the early Earth. And that's because the accepted theory right now about the first glance of life on Earth is about a mix of what was present on the planet and what arrived from outer space, so from comet, from space dust, and whatsoever. So understanding these processes becomes somewhat crucial. Now, our group, during the years, has been able to characterize many ionic species and cations, for example, N2O2+, C2H22+, or CO22+. And those are species with a great relevance at an atmospheric level. For example, CO22+ is considered to be the responsible for the lack of O+ concentration in the atmosphere of Mars, due to a Coulomb explosion of the molecular dication, energetic enough to give to O+, an high enough escape velocity from the atmosphere. And this has been verified by Mariner 6 spacecraft and Viking 1 lander. Now, to understand these processes, we of course have to simulate them and recreate the conditions for the reaction to happen in the same way it's happening in nature. So our job is to have an effusive beam of the target molecule crossing with the light source of the right energy, and then to detect and study the various processes that are happening. But what kind of information we aim for? Well, first of all, the energy thresholds for the different ionic products formed, the related branching ratios, and the angular and energy distribution of the fragment ions at different photon energies. All these lead to the study of the potential energy surfaces of the relevant electronic states, characterizing the dissociation dynamics of the investigated dications. Now, all these informations can be extracted as raw data from our experimental setup, which is based on the angle-resolved photoemission spectroscopy, or ARPES, which is a technique that allows us to perform a photoionization study using a tunable and high photon flux of a third-generation synchrotron source, in particular the one from Electra, which is located in Trieste, Italy. Now, the experiment is mainly based on the use of a PepiPico detector, in which PepiPico stands for photoelectron, photoion coincidence, and the detector is coupled with a time-of-flight mass spectrometer designed in order to measure the spatial momentum components of product fragments in the experiment. The end station of ARPES is equipped with a funnel-type MCP stack with the Z-mounting assembly, and the sample is admitted through a non-magnetic hypodermic needle in the interaction region of the mass spectrometer. In the right corner, you can see a photo from above of Electra facility in which the experiment has been done. And this facility can provide a monochromatic, highly collimated synchrotron light beam that crosses at right angles our effusive molecular beam. And the ion products are detected in coincidence with photoelectrons. Now, going into details about the experiment we made, we chose a lean for a series of reasons. First of all, is a small molecule, which is the first member of the cumulin series CNH4. And the odd molecules of cumulin series belong to the D2D symmetry group and can exhibit axial chirality. even if it has not been detected directly yet in the interstellar medium, due to the fact that it does not have a dipole moment. It's thought to be present at an interstellar level, and it's closely related to CH2CCO, which is an important transient molecule that has been detected in the interstellar medium. And moreover, an experimental and theoretical investigation of double and triple ionization of Alene has been carried out recently by John Eland and Raymond Feifel's group with the technique of the magnetic bottle. And this led us to deepen the study of such molecule. At the moment, I'm here in Gothenburg, in Sweden, with Raymond Feifel's group. So we are investigating other molecule with this technique, actually. So our target molecule, Alene, has a low first ionization energy, which is 9.69 electron volts. So we recorded the spectra with a photon energy range going from 22 to 45 electron volts. And on the left, you can see the single ionization spectrum of Alene, and on the right, an actual coincidences plot with the two time of flight values of a couple of ions produced report on the X and Y axis. And they are actually the two red color spectra. And parent cations and ion-ion coincidence efficiency curves are obtained with a small energy step from fixed energy spectra in order to measure the appearing potential for the decation, and thresholds for the dissociation channels and their branching ratios. Here you can see reported two spectra recorded both at 40.8 electron volt. But the top one is the single ionization spectrum we saw on the previous slide, while the one below is the one relative to the double coincidences, from which reporting the two time of flight values of a couple of ions produced in the same photoionization event on the two axes, one could define a point. By recording the spectra for all the energy range we defined, we have been able to identify several fragmentation channels, including the one responsible for the formation of the Alene dication. The energy value at which the dication should appear was previously reported to be around 28 electron volt, and we confirmed that value, finding the energy to be 27.8 electron volts circa. And here we can see a much more detailed focus on the actual identification of the energy threshold for the molecular dication appearance in the spectrum. In the first place, we set the energy value above 28.5, but then we decided to record various spectra with a more fine variation of the energy on the order of the 0. electron volt. And then, using a Gaussian fitting within a defined range, we estimated the limit of detection, a lot, for the peak, stating the incipient formation of the dication from 27.8 electron volt. Here you can see reported other channels that are appearing at different energies going up in electron volt. On the right image, you can see a coincidence spectrum recorded at 40.8 electron volt, in which all the fragmentation channels are open. The more concentrated areas are, of course, the zones with more coincidences, and these defined points are the first step to define energy thresholds, scarce, branching ratios, and so on. And starting from the coincidences plot, one can extract all the information we need, considering that two time of flight values define a point, since they are produced by the same photoionization event. And it has to be clear, though, that not every point defined in the graph is coming from an actual event. There are some events called false coincidences that can arise from various sources, as oscillations in the current, as ground, as impurities that can be present in the sample. So in our case, our sample was commercial, so it was pretty pure, but the purity stated was of 95%. We in fact detected some small peaks, and the molecular one at mass 56 that we have attributed to cyclobutane. And all these false coincidences have been subtracted for the analysis to properly obtain the peak dimensions, the peak shapes, and consequently the kinetic energy releases. An interesting feature that we can clearly see, thanks to our setup high resolution, are the traces that we can see starting from the coincidences between mass 1 and mass 39, 38, and 37. And these traces show the formation of a metastable dication during the dissociation. And this is extremely interesting because the metastable traces have already been detected previously, but not with this resolution. And this has been a thing that we decided to investigate further, collecting data for a long time at a fixed energy, 36 electron volt, with a low gain to be sure to highlight the traces without having too much ground and false coincidences. And moreover, we defined, and we are still trying to refine, a Monte Carlo simulation to estimate the lifetime of the metastable dication during the dissociation. Here you can, in these two coincidences plot, we can really appreciate better the traces because we have a lot more statistic. And the collection of this data went on for more than 24 hours. And what is extremely interesting is the detection of a further metastable trace occurring at mass 3. So it's a coincidence involving involving H3 plus, so the possible roaming of nitrogen. And as you can see, we tried simulating the whole trajectory of the main trace, but we did it also for the others, of course, for the other traces, using an arbitrary lifetime at the start and an arbitrary number of trajectories and fixing them along the course of the simulation to adapt it to the experimental data. And the one reported as a time of flight, as tau of 0.16 to the minus 6 seconds with 10,000 trajectories used. But of course, the simulation and the analysis is still going on, especially because of the subtraction of false coincidences and ground in the final part of the trace, which is really the tough part to get rid of all the false data. In this slide, we can see reported threshold energies for the main fragmentation channels, producing H plus, H2 plus, and H3 plus. On the x-axis, there's the energy range in which the spectra have been recorded. So here you can see clearly at what energy a specific channel begins to show. And furthermore, this data can be compared to obtain the branching ratios that are the expression of the specific weight of every ionization channel at a specific energy in terms of how many coincidences are due to that channel in respect to another. And of course, all the channels, the most interesting ones are these ones, the ones shown here, especially the one regarding H3 plus, in which has also been detected a metastable tail. In conclusion, these preliminary data are still under an ongoing analysis, but the aim is the determination of an angular and kinetic energy distribution of fragment ions at different photon energies, the refinement of the simulation to estimate the most correct trajectory and lifetime of all the metastable traces highlighted, and the estimation of the beta anisotropy parameter in order to completely characterize the microscopic dynamic of the fragmentation reaction channels. Now, what could we do next? So in the first place, we are aiming to improve the theoretical efforts to calculate the potential energy surfaces of interest, investigating the location of the lowest stationary points of the B3 lead level of theory using this basis set, the 6311 plus GD. And then, well, Aline is just the first and smallest of its series. Its derivatives and some molecules similar to it could be maybe the targets of future studies using the knowledge and information acquired from the study of C2H4. So in the end, I would like to thank the University of Perugia, in particular the Department of Civil and Environmental Engineering, the gas phase staff of Electra Synchrotron Facility, and of course the organizers of ICCSA 2023 for the possibility to present this work today. Thank you.
Thank you, Marco, for this presentation. We have a couple of minutes for questions, curiosity. No questions, so probably everything was clear. Okay, let's thank again Marco. We now change session to finish the computation of the chemistry session. Prendo.
Certo. Vuole sedersi al mio posto.
Non sapevo. Dovrebbe esserci.
Alla sala. Aspetta.
This is the last part of the PC IoT workshop. Thanks to Marco for leaving with me the speech. And I will present the last two papers of the PC IoT workshop, Privacy in the Cloud Edge IoT World. And is Arasalaga, I think, if I well pronounced, with the paper SHIMED, an application on secure computation or medical cloud data based on homomorphic encryption. You have 15 minutes and 5 minutes for question and answer. You can begin. Okay. Good one. Okay. You can begin, Professor Salaga.
Yes, hello everyone. Let me share my screen.
Okay. Così la zappo proprio.
Credo che dipenda da lei.
If it's possible, you speak loudly because the voice is very loud and the volume is at maximum.
Yes, of course. So, good morning from Patras, everyone. Can you see my screen?
Yes, we can see your screen.
Great, thank you. Good morning from Patras, everyone. I would like to thank you in advance for joining me today. My name is Hara Salaga, and as a graduate of University of Patras, along with my professors, Dr. Karanikolas and Dr. Kaklamanis, we have collaborated to develop CMED application, which I will present you today. Our work CMED stands for Seal Homomorphic Encryption on Medical Cloud Data. For starters, let's outline the points we will cover in today's presentation. First, we will begin with the definition of homomorphic encryption, exploring the different categories and discussing the security it provides. Also, we will introduce Microsoft Seal and the EVA compiler, which we utilized for implementing this application. Next, we will delve into the realm of cloud computing, discussing its security aspects, and we will focus on GCP as the chosen provider for storing our data. Moreover, we will delve into the relevant researches and examine the app scenario, providing an analysis of its architecture and components. Finally, with screenshots, we will showcase the end-to-end experience in the application's environment. And last, we will outline future work that will be undertaken in the field of homomorphic encryption. So, what is homomorphic encryption? It is considered as an innovative method which allows mathematical operations to be performed on encrypted data without requiring decryption first. It can be either symmetric or asymmetric, and the diagram illustrates the application of these encryption types. For our own implementation, we focused on asymmetric encryption. As you can see, the user generates a keeper consisting of a private and a public key, and then the user uses the public key to encrypt his data before sending it to the cloud provider, who perform computations on the encrypted data. The users then can retrieve the encrypted result and decrypt it with their private key. Generally, there are three types of fully homomorphic encryption, and these are fully, which support an unlimited number of both additions and multiplication operations on encrypted data. This category is considered as the most powerful form, but it is also more computationally intensive and challenging to implement. Somewhat enables the evaluation of limited number of both addition and multiplication operations on encrypted data. And lastly, partially allows the evaluation of either addition or multiplication operations on encrypted data. Let's see in terms of security the power of homomorphic encryption and the flaws that may exist. Most homomorphic encryption schemes are based on ring learning with errors, which are designed to protect against attacks from quantum computers. Also, performing multiple mathematical operations on encrypted data makes it challenging for third parties to extract the original ones. And of course, the fact that the private key is not shared mitigates the risk of data exposure. Now, the reasons why this encryption is not widely used are encountered to the accuracy, which is difficult to maintain given the complexity of computations on encrypted data. This may result to errors, of course, Then the limited support, since it is still an emerging field, there are a limited number of libraries available to support its implementation. And computational complexity at last, which makes homomorphic encryption techniques slower compared to traditional methods, which is a major issue if you have to deal with big data. So a famous library that implements homomorphic encryption is SEAL. It was proposed by Microsoft and it is implemented in C++, and its installation is done through the CMake tool. It implements the CKKS scheme, which refers to decimal data, where there may be a small deviation in result accuracy, and the BFV scheme, which refers to integer data. And with SEAL, we have the ability to generate keys and various files for encryption and decryption processes. We continue with the EVA compiler that exclusively implements the CKKS scheme, and our application implementation is based on it. The methods implemented by EVA include the encoded program and signature generation, the parameters for public and private key, and last, the scales and ranges, where scales refers to controlling the level of noise introduced during the encryption processes, and ranges define the maximum value representation of the encrypted data. Balancing these two factors is critical to ensure the accuracy of our data in general. So we move on to the introduction of cloud computing. According to NIST, it refers to a dynamic model of services such as servers, databases, and etc. The key characteristic of cloud computing is the rapid adaptation and provisioning of resources based on user demand. In terms of security, in the data lifecycle, there are three critical states: transfer, usage, and storage, where data are the most vulnerable. Since the cloud provider is responsible for managing responsibility, this means that users have limited control over the usage, the storage, and of course the location their data are. Since most of the cloud providers create the encryption keys without the involvement of users, is making them concerned about their data integrity. The bring your own key is being adopted by some providers and allows users to use their own encryption keys in the cloud provider. Then the GCP is the platform that we use for implementing our application, and it provides services like Google Cloud Storage, which we used for storing our data in a unified bucket. We created a virtual machine with Ubuntu 22.04 LTS as the operating system. And to ensure network security, we defined network rules that allowed us to control internet traffic effectively and define the IP of our machine for communication on internet. For key management, we use the bring your own key technique, as I mentioned earlier. Before moving on to the CMED scenario, let's see some researches that exist and have implemented homomorphic encryption in their core. The first one refers to the implementation of a fully homomorphic encryption scheme in the cloud. They use the AWS as the cloud provider, and they simply present their data from an IDE environment and the storage of them in the AWS. In the second one, they have created a health system by monitoring ECG data using Amazon and fully homomorphic encryption scheme for their implementation. The last one examines the processing state, which is considered as a critical state for data security, especially in cloud computing, where they proceed with the analyzation of three partial homomorphic encryption methods. So now, without further delay, let's dive into the concept of our application. CMED consists of the usage of SEAL library and the aim of Google Cloud Platform. And what it does basically is that the data storage in the cloud from the doctors for their patients, this is one of the following performance, and the quick retrieval of the uploaded encrypted data without the fear of loss or alternation, and of course the processing on encrypted data in cloud using polynomial operations from which a doctor can determine the patient's health. Moving on to the background of the implementation, it should be noted at this point that we have made an assumption based on breast cancer data obtained from an online dataset. These data follow a normal distribution and are approximated by the following polynomial with a mean of 0.1137 and a standard deviation of 0.05689. As we can see from the graphical representation, the values within the purple range indicates that the result is benign, so no further investigation is needed from the doctor's side. And in the other two cases, a further investigation is needed since or probably the therapeutic approach must be changed. So let's see the system architecture of our application. Starting from the UI, which is creating with React framework, is first responsible for authenticating users through Auth0 cloud-based platform. Users are stored in the database that Auth0 provides so that they can view the functionalities of the application. In client side now, our users keep locally their encrypted file and their original data, of course, and they use the CLI that we have created in order to generate the appropriate keys for encryption and decryption processes. As long as the backend system concerned is built on the Flask framework, which empowers the front-end to generate and transmit HTTP requests via a REST API, these requests then are processed by the backend system. Our backend system is on GCP, of course, and in the virtual machine, it's the place where the encryption processes are taking place. And it communicates, of course, with storage and where it retrieves files from the patients. Last, in order to ensure the application security on the internet, the use of a reverse proxy called CADI is required. Let's see some details about the PyEva CLI. It's an executable file that is located in the user's side. And what it does is basically generate keys, private and public, through the key generator function, and the encryption and the encryptor and decryptor functions in order to encrypt and decrypt the files that sends to cloud. So the process of fully homomorphic encryption is where the whole magic comes in place, and primarily an input polynomial program is created using PyEva, where 16 test results were selected. Then this program needs to be compiled from compile CKKS method, where we define scales and ranges, and the signature and parameters have been created too. Then based on parameters, we generate the key pair. Now we can encrypt our original data in order to send them to cloud using our public key. And then we proceed with the execution of the encrypted data with the aim of compiled program and the public key. This process is going to take place only in cloud. And last, we decrypt our private data using our key that we have never shared with the cloud provider. So in the UI and Auth side, in order for a doctor/user to use our application, it is required to be an authenticated user, as we said. Every user should register, and there is a database contain all users so that they can use the rest of our functionalities like create patient, list patient, download file, or upload file through UI.
5 minutes left.
Oh, yes. The identification of doctors in the backend system is performed through email using JWT. Then in Cloud VM, we have used SEAL library to perform operations through Executor. And back at the appropriate folders are created for the doctors. And at this point, we should mention that doctor is aware only of his patient's data, and he has zero knowledge about the rest of users. So between the VM and storage, encrypted files are exchanged, and the doctors shared through the application. To ensure secure access from the internet, the placement of security keys is required to protect against malicious actions. For this purpose, the CADI server leverages the HTTPS protocol to provide protection against man-in-the-middle attacks. Our unified bucket is the medical IVA here that we store all the users' information, the doctors. So here for Hara doctor, we have these two patients separated in folders. And now let's see the environment of our applications. So here we have the home page where a user can only log in or sign up in order to proceed with the functionalities. And this is our sign up and login pages where a user has to use his own credentials or just log in from his Google email account. Secondly, now the user is able to see all the functionalities that our application has, starting with download CLI, which is our executable responsible for key generation, encryption parameters, and the program that we based the CKKS scheme. So we have three different cases for existing users who want to encrypt or decrypt their data, or for a new user that he wants to just generate the keys and the encryption parameters. For the file upload section now, our doctor can select some of his patients that he has already created or just create a new patient and upload the necessary files that he wants. We have to mention here that the allowed types ensures the fact that our user is never going to share his private keys or parameters in the cloud. Now we can see a pop-up window here where our data has been uploaded successfully, and we can select the date of if we want to proceed with the execution of this data. So in the download file section for our patient, we can select one or more files to download from the cloud. And then what our users will see is an Excel file with the results of 16 categories of 6-digit accuracy examinations. And small presentation of them is right here. And then the results and classification on situation based on the original data, results, and finally the conditional that has come up from the results. Then the mean squared error is the minimum achievable error according to the defined scales and ranges required by the EVA compiler, and is right here. So the outcomes of our work is that we believe that we have created a user-friendly application with guaranteed ease of use. The confidentiality, availability, and integrity is achievable. Confidentiality through authentication from the Auth0 platform. Availability because our user can store and retrieve his data whenever he wants. And integrity because our user doesn't have to have a fancy system to apply any kind of operations that he may want in the data of his patients. And for the future work, we believe that the enhancement of the functionality of fully homomorphic encryption schemes will be adapted from more and more businesses and scientific factors, of course. And with the introduction of quantum theory, stronger security, higher computational efficiency, and the ability to perform more complex computations on encrypted data will be achievable. Also, the capabilities that offers us will be adopted from more and more applications. Last but not least, the MPC allows multiple parties to jointly compute a function of their private inputs without revealing those inputs to each other. This can be enhanced with the development of new homomorphic encryption schemes. Are there any questions?
Questions?
I would like to thank you again, everyone, for your attention and time.
I have one.
Yes.
Have you experimented the performance issues? Because fully homomorphic encryption is known for time consuming and CPU time consuming. What's about the performance issues?
You're totally right. Yes, when we try to do a homomorphic encryption in our environment without the aim of cloud, then we experienced a lot of time issues because it was not easy in our environment. However, in cloud, we could define just a virtual machine that with a lot of memory and CPUs, of course. So it was a more easy approach in there.
Okay, that's it. Other questions? Thank you very much. And here I present the last paper of the workshop. The presenter is Antonio Scarfo, and the paper is Prevention of Cyber Attacks and Privacy Breaches in the Healthcare Sector. Antonio, you can go. 15 minutes for the speech, 5 minutes for the lecture.
Yeah, hello everybody. I will be shorter if possible. Let me try to share my screen. Could you see my screen?
Yes, we can see it.
Good. Okay. The paper is the title of the paper is Prevention of Cyber Attacks and Privacy Breaches in Healthcare Sector. I am a student in a PhD courses at the University of Salerno. Just a mention for the co-author that I've collaborated and I'm honored to working with. And then I want to go through the presentation in order to show you the work we did. Okay, the basic question related to the paper is it's possible to rely on high reputed reports to prepare my defense in cybersecurity and so reduce the risks with some proactive actions. In order to investigate this question, we did a on-field test. First of all, the relevance of the methods is very high because we did this test in healthcare environment, and as we can see from a report of IBM, the healthcare environment is the most pay the highest cost to data breaches, and these costs are growing year by year. What we did, we take in consideration basically three highly reputed reports. The reports from ENISA, that is the Agency of Cybersecurity at European level. This is a super report. They collect reports across the world and summarize the most important insights. Then we take in consideration CISA report, the Agency of American Government, where is ranked periodically the top routinely exploited CVE. And finally, the EPSS report. This is a more live report that report a predictive reports for the CV that is likely to be used in next future. So the infrastructure we used to do this test is in the slide. This is a campus of a university with is hospital, and we can see in this slide several points of control of security in especially a couple of cluster of firewall. We did several tests, but basically we focused the attention on the report 2, a test we did on the couple of firewall at between the whole campus and internet. Given that this firewall in the circle, given that this firewall are coming from Fortinet, we included another report coming from the vendor, a global threat landscape report that ranks the top vulnerability that the vendor can see over the world, around the world, and this is a relevant sample because Fortinet counts something close to 40% of the firewall shipped around the world. So the first insight that we can have comparing the CISA, the Fortinet report, and the ENISA report, where we collect the top 20 CVE from CISA, the top 20 CVEs from Fortinet, and we had to pick up the most relevant CVE from ENISA, which does not rank the CVEs. We can see that the CVEs in common among between Fortinet reports and ENISA and CISA are very small. A couple of CVE with ENISA, just one CVE with CISA. On the other side, the CVEs in common between ENISA and CISA are relevant 8/20, about not so relevant, but interesting insight. This is for the reports. Then if we include the data from the field, we can consider APSS also like a data from the field, not just from our architecture, but over the world, because the APSS score is calculated by the sort of threat intelligence that collect information in real time. So the CVE collected by APSS are more fresh, more actual, more relevant. On the other side, leveraged infrastructure that I showed before, we collect 75 CVEs organized in this report are 60 and organized by criticity. According to CVSS version 3 rating. Okay, if we compare the information we collect, we can see that the CVE in common among between ENISA, CISA, APSS with the report from the field are basically a low number, because we have some percent related to the total CVE analyzed, and 10 to 20% in the case of APSS related to the critical CVE most risky. So the most important intersection among reports we can expect in some way is between the Fortinet reports and the reports from the field. Then, in some way, we can use the CVE to prepare our defense using, for instance, Mitre attack model. Because if I knew the CVE that could be exploited in my environment, I can understand what kind of tactics and techniques the attackant can use, and then I can prepare myself against these tactics. But if I take in consideration the results of the analysis, just a small part of the CVE exposed, announced by the reports are we can see in the live environment. So it's not so useful to at the end of the day to use this report to prepare my defense. This is the conclusion of the article, and I think that I'm in time and open for question.
The low time consuming presentation. There are questions? Any questions? Okay. Thank you very much.
Thank you.
This was the last paper of PC IoT workshop, and I'll say you goodbye. And I think the next year will be another workshop, same workshop the next year. Goodbye.
Goodbye.